Okay, I'm now going to speak about residue theory, and this is what all the other videos have been leading up to. There's a very nice way of calculating contour integrals using what's called residues, and this is connected to the idea of a Laurent series. So recall that if you have a function f, so let's say f has an isolated singularity at z0. If f is analytic in some annulus which surrounds z0, like the green region I've shaded here, so the inner circle radius r, outer circle radius capital R. If f is analytic in that green region, then I can write f as a Laurent series. So as a series which could possibly contain negative powers of z minus z0. So this we know so far. So what's a residue? Well, uh, let me say it like this. The coefficient of, well actually let me write it like this. The coefficient c negative 1. So you see Cn, where n can go from negative infinity to infinity. So when n equals negative 1, you get c minus 1. That number is called the residue of f at z0. So find the Laurent series of f at z0. Take the coefficient of 1 over z minus z0, and that's the residue of f at z0. And we write the shorthand notation for this is c of minus 1 equals res f comma z0. Okay. Now you might remember from the very first video I did in this series that we have a formula for Cn. So using that formula, I know that actually the residue of f at z0 is given by 1 over 2 pi I contour integral around c of f of z dz, where c is, well, it's any closed contour in that green region which surrounds z0. So could be something like this. Yeah, evaluate the integral of f of z around c, divide by 2 pi I, and that would be your residue. Okay, now this is why I spent a fair bit of time in the previous two videos doing examples regarding isolated singularities. Because if you know what sort of a singularity you have, it makes it very easy to calculate the residue. You want to avoid sort of evaluating this contour integral. So if your singularity z0 is removable, then actually the residue at that point is 0. Nice and simple. If z0 is a pole of order m, okay, actually let me write as a pole of order m plus 1. It'll make the formula easier to remember. Then the residue at z0 is defined to be 1 over m factorial limit as z approaches z0, the mth derivative of z minus z0 to the power of m plus 1 times f of z. So take z minus z0, raise it to the power of m plus 1, multiply that by f, differentiate it m times, take the limit as you go to z0 and divide by m factorial. That would be your residue when you have a pole. May look complicated, but it's not really, because often you get a simple pole or a double pole, or maybe at worst a triple pole. So it's not as bad as it looks. So in fact, if you have a simple pole, then m would equal 0 in this formula. So the formula for a simple pole would become 1 over 0 factorial, which is 1, limit as z approaches z0, 0th derivative, so we do nothing, z minus z0 times f of z. Yeah? That's for a simple pole. Now, if you have an essential singularity, then as far as I'm aware, there's no shortcut. So in that case, if you want to find a residue, you would have to literally compute c minus 1 by hand. That doesn't necessarily mean that you have to do that integral. What you could do, you could just find a Laurent series, like we did in previous videos, and then just see what's the coefficient of 1 over z minus z0 in that Laurent series. So that's often what you would do in the case of an essential singularity. Now, the big result now is what's called Cauchy's residue theorem. This is really something, actually, this result. I mean, you thought the other Cauchy results were good. This one is just on another level. Okay. So, what are the conditions for this residue theorem? So, suppose you have a simply connected domain D. So that's the first thing you need. Remember, what's a simply connected domain? A domain without holes. And you need a function f that's analytic in D, except at a finite number of singularities. So your function is allowed to have issues, if you like, at a finite number of points in D. Okay, so let me draw you an example. Let's say this is a simply connected domain D. I drew something without holes, and my function f is analytic everywhere inside D, except at maybe a finite number of points. Let's say here, 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 something like that, right? And I'll label these. So I'll call this point Z1, this point Z2, this point Z3, etc., etc., etc. Alright, so here's the big theorem. I hope you're ready. If you take some contour lying in C, now, actually this is very important. C should not pass through a singularity. It's allowed to pass around a singularity, but it can't go through one. So let's say I draw C like this. And you have to draw it so that it goes in the anti-clockwise direction. Okay. Then the contour integral around C of f of z dz is equal to 2 pi I times, you take all those singularities that lie inside C, So consider Zj inside C, and you calculate the residue at those points. And if you add them, you magically get that contour integral. So it's really something. So in this case, as you can see, that C that I drew, it sort of contains 4 singularities within it, right? So if I wanted to calculate that contour integral, I would find the residue at those 4 points, add them together, multiply by 2 pi I, and that would be my contour integral, right? Now obviously if there are no residues within C, then there's nothing to add and the integral is going to be 0. We know that by Cauchy's integral theorem anyway, right? If you have a closed loop and your function is analytic in that loop, then of course the integral is going to be 0. So that's our result. Let's have a look at some examples. Now, a lot of the examples that I'm about to do, you could do it using Cauchy's integral formula, or the extended version of Cauchy's integral formula. But now that you know about residues, you can take all those questions you had before and do them all using this method. And, of course, integrals which you couldn't do before as well. So, first example that I'll do, I want to compute integral of sine z on z, and I'm going to go around the unit circle dz. Okay, call my function f of z. Where is my function? Where does it have a singularity? When z is equal to 0. It's undefined at that point, so that's my singularity. What does modulus of z equals 1 look like? As I said, it's just the unit circle. Okay, let's pretend that's a circle. So this is 1, 1. So as you can see, the only singularity within C, or within z equals 1, is at z equals 0. So therefore, this integral is going to equal 2 pi I times the residue of f at 0. Now what's the residue of f at 0? Well, note that limit as z approaches 0 of sine z on z, if I use L'Hopital's rule, that equals limit of z that equals limit as z approaches 0 of cos z on 1, which equals 1. So I can make f continuous at 0 by defining f of 0 to equal 1. Therefore, z equals 0 is a removable singularity. And remember, when it's removable, the residue is 0. So this means residue of f at 0 is 0. Therefore, integral along the unit circle of this function is equal to 2 pi I times 0, which is just 0. That's it. Let's have a look at another example. Compute so now we'll take the circle of radius 3. By the way, when they don't mention which direction the curve is being traversed, you assume it's counterclockwise and anticlockwise. So in the previous example, because I didn't mention in which direction the unit circle is being traversed, you assume anti-clockwise. Same with this question. So now I want to do the integral of z on 16 minus z squared, z plus I, dz. Okay, so where is this function going to have singularities? When the denominator equals 0, and that's going to be when z equals negative I or plus or minus 4. So let's draw those points on the complex plane. So I have z equals negative I should say actually, which will be like somewhere here, and at 4 and negative 4. Okay, and now I have to draw a circle of radius 3. Okay, so this point here is 3. So as you can see, the only singularity that's contained within my curve is at negative I. So I only need to calculate the residue at that point. So this one, again, if I call this f, so integral f dz will equal 2 pi I times the residue at f evaluated at negative I. Okay, it's not too hard to see that z equals negative I is a simple pole of f. Right? You can easily see that. So then, if I want to figure out the residue at negative I just use my formula. So residue of f at negative I equals limit as z approaches negative I, it's going to be z minus minus I times f of z, which will be limit as z approaches negative I of z plus I on f of z, which equals limit as z approaches negative I of z on 16 minus z squared. If you just plug that in, you would get negative I on 17. So going back to here, the value of this contour integral is 2 pi I times negative I on 17, which is going to be 2 pi on 17. So that's how you would do that contour integral. It's that simple. You draw your curve, you locate the singularities that fall inside that curve, you calculate the residues at those singularities, add them, multiply by 2 pi I. Simple as that. Let's have a look at another example. So now I'm going to compute integral of cos z over z minus I cubed dz. Okay, again, I'll call this function here f of z. I'm going to draw the curve which we're integrating around. So what are we integrating around? It's modulus of z minus I equals 1. So it's centered at I. It's a circle centered at I and its radius is 1. So it's gonna be here, isn't it? So if I draw a circle. Alright, let's say that's a circle. So this is going to be my curve. Alright, now where is my function? Where are my singularities? My singularities are when the denominator is 0, so that's precisely when z equals I. And in fact, it's easy to see that z equals I is going to be a triple pole. So F has a triple pole at z equals I, which is the only singularity inside the curve. So by Cauchy's residue theorem, that integral is going to be 2 pi I times the residue at I. So we have to calculate that residue. Note that the residue of f at I, according to the formula I gave a few moments ago, this is 1 over 2 factorial, limit as z approaches I. It's going to be second derivative, z minus I cubed, f of z. Now 1 over 2 factorial is just 1 over 2. Now what are we going to differentiate twice? Well, if I multiply z minus I cubed by f, I'm just going to be left with cos z, right? So let's see, if I differentiate cos z twice, if I differentiate once I get negative sign, differentiate one more time I get negative cos. So I guess this will become negative a half, limit as z approaches 0 of cos z, which will become negative a half cos of I, and I can write that as negative a half cos of 1. Right, here I'm using that result that says cos of IY is just cos of y when y is real. Okay, so I know my residue. It follows by Cauchy's residue theorem. I can say that integral f of z dz is equal to 2 pi I times minus a half cos 1, which equals minus pi I cos 1. That's pretty much it. Let's move on to the next example. Make this one a little bit harder. Although that's not really possible, as you can see, the whole beauty of this theorem is it makes life so easy. Okay, I'm going to compute integral around circle of radius 5. I'm going to take my function to be this. So up until now, if I wanted to do something like this, I would have to use partial fractions and use Cauchy's integral formula. Or if I wanted to avoid partial fractions, maybe use Cauchy's integral theorem for multiply connected domains. Both are kind of a hassle, but this is going to be a lot easier now. So if I draw the region where I'm integrating, so let's draw the the complex plane. Then I draw a circle of radius 5. Okay. Alright, so this is 5, 5. Now, where is my function? Where does it have singularities? When the denominator is 0, which is at 3 and 4. So at these 2 points, okay, this is not the scale obviously, but at those 2 points, 3 and 4, I got singularities. And they both lie inside that circle. So I will need to calculate the residue at those 2 points. Again, it's simple to see that z equals 3 and 4 are simple poles. So as you can see, the important thing with all this is being able to classify singularities well, which is why I spent a fair bit of time on it in the previous videos. Once you got that down, things become very straightforward. Anyway, I can see that these are going to be simple poles, and they both lie within z equals 5. Okay, so it follows that the integral is going to be 2 pi I times the residue at 3 plus the residue at 4. So I just got to calculate those two residues. And I can use the formula for simple poles. So if I use that formula, I know that residue of f at 3 is going to be the limit as z approaches 3 of z minus 3 f of z, which is limit as z approaches 3 of 1 on z minus 4. Plug that in, you get negative 1. Now, residue of f at 4, I should say, that's the limit as z approaches 4 of z minus 4 times f of z. So that's going to be the limit as z approaches 4 of 1 on z minus 3. That's going to be 1 on 1, which is 1. Therefore, this integral is going to be 2 pi I times 1 minus 1, which equals 0.